Welcome to the lecture Applied Multivariate Statistics at the University of Koblenz-Landau in 2015 and 2016. My name is Ralf Schäfer. I'm junior professor at the Institute of Environmental Science in the university. I'm junior professor for quantitative landscape ecology, and I'm teaching statistics in a master course, as you have noticed, GIS on bachelor master level, environmental modeling bachelor master level, and aquatic ecotoxicology in the master level. My research interests or current research projects involve effects of toxicants in freshwater ecosystems, particularly on invertebrate communities, aquatic invertebrate communities, and on ecosystem functioning, as well as associated microbial communities. Trade-based aquatic ecology, so focusing on particularly on anthropogenic stressors and climate change. The questions here are, can we use traits of organisms such as the body size or the generation time to detect effect of stressors, perhaps even stressor specific, and predict related community changes? And finally, trophic linkages between aquatic and terrestrial ecosystems. A couple of more research avenues. I'm not going into details here, but have a look on our website, landscapeecology.uni-landau.de. What we do is primarily field studies and field experiments, but sometimes we also do laboratory studies to confirm our observations from the field, and we do data analysis and modeling to capture patterns and find relationships in big data sets, for example, between the toxicant exposure and changes in communities, and try to find out how important toxicants are in comparison with other stressors. We have a course assistant in this course who's also teaching here. That's Eduard Söch. He's a PhD student in our group, and he will help you with our code and also give some part of the lectures. Some organizational issues that are not relevant for people outside of the university. Note that this is the second part of the course. The first part only deals with univariate statistics. However, you should still be able to follow this part of the course even when you have not participated or have no access to the first part of this course. The organization for people attending this course at the university is that we have two groups. One group Monday 8:30 to 10 o'clock, another group 10 o'clock to 11:30, and you will receive email information over clips. So it's important that you join the lecture in the online system of our university. You should have been taught how to do this. There's lecture material. I provide you the link here to the website. However, for those outside, you will find the link as well below the videos. And for those inside university, I will send you the link as well, so you don't need to copy the link here. What do you need to do to obtain a proficiency certificate? Well, you need to actively participate in the course and in the exercises, and to have a successful exam after. The course date has been set to the 24th of March 2016. The whole lecture follows the inverted classroom design. So that means that you have videos and screencasts to enable you to study at home, so to listen to the lecture and follow the demonstrations. The advantage is that in comparison to a typical lecture, first of all, you can cut the lecture into slices. So when you need a break, you can make a break, or you can repeat parts of the lecture that you haven't understood. You can consult books or whatever you need, and the slides to learn beside listening to the lecture. And what we will do in classroom is rather to have you working. That means you need to ask questions on topics that you didn't understand, note that of course that should not be general questions like I didn't understood what the whole course is about, I didn't understood what linear regression is or whatever. That should be very detailed questions on specific issues. So you shouldn't go to the course and expect that you learn anything if you haven't done your self-study time at home. That's really important to understand. In addition, we will have exercises in R, so practical application of the knowledge. And again, this requires that you work before at home, otherwise this will be very useless for you. So we have about 1.5 hours contact time per week that can be extended if necessary, and we have an own study time at home of approximately 1 day per week. Please take this 1 day per week. Some people may be quicker in grasping the material, others need longer. So check out what type of person you are, how much time you need. And a quick overview on the relation to other statistical courses is provided on this slide. For those people that have studied the bachelor course at our university will see that in the Bachelor of Science course you have an introduction to probability theory and statistics, and in the Master of Science level we have the univariate statistics and exercises, or the course that you have just passed, and we have the multivariate statistics and exercises course that you are now attending, the first part. So the course is generally organized according to learning objectives, these general course objectives. So each week you will see some learning objectives for the particular course that you can use for revisiting and studying at home, and I will also provide you with questions to these objectives so you can test and check whether you have met the learning targets or you're still lagging behind. If you're lagging behind, then you need to do and to work more. So what general course objectives are: to understand the different types of statistical approaches, to select the appropriate statistical method for a research question that is given, to have a moderate level of statistical modeling skills, and basic skills in R, including the development of scripts. What are my expectations? As I stated before, active participation is crucial in this course. You have to study at home. You can go through demonstrations, you can repeatedly go through them, and you should put down questions that we will discuss in classroom then. If you're not doing this, then the time is wasted and you won't learn much in class. Same holds for the R exercises and demonstrations. Self-assessment of the learning progress based on the intended learning targets, using the review questions and exercises. What does this mean? You will, as I already mentioned, obtain some questions, some review questions and exercises, and I will randomly choose students in the next session, and ask these questions. So it will be kind of a shame for you if you are not able to answer these questions if you are selected. Yeah, the course uses the software R. If you have participated in a previous course, you've already may have learned why R has been chosen. R is generally a program that has massively expanded in the last decade. I started working with R in 2004, 2005, and the contributions to this statistical learning environment or statistical programming environment have massively expanded in terms of packages provided by contributors. So in R nowadays you have really everything that you need for data science, data analysis, so you can access databases, you can do statistics, you can do graphics, and you can easily communicate with other programs such as GIS programs, as you may have experienced in other courses by me. We faced R with GrasGIS or with database program PostgreSQL, for example. That's what we use at our university for geodatabases with PostGIS. So on the figure here, you see the number of Google Scholar documents for each software, and you have here JUMP, Minitab, Stata, Statistica, Systat, and R, and you can clearly see that from 2005 onwards, R is growing steadily and is now one of the programs which has the highest citations in Google Scholar. Nevertheless, what is omitted from this figure is SPSS and SAS that are still both hold the top positions, the first and the second positions, SPSS and SAS. Nevertheless, they drop from about 200,000 to 75,000 in 2013. So still 3 times higher than SPSS is still 3 times higher than R, but nevertheless R is picking up, and if the decline of SPSS continues, it will be R will overtake SPSS. We have another figure here. When you look at traffic on email discussion list, you can really see that R is here the dominant program. It's really among dominant statistical packages overall, and for the email discussion, the traffic R actually is much higher than Stata, SAS, or SPSS. You can see more stats related to the popularity of R under this web page link. Well, and to end this justification with a quote from a New York Times article by Max Kuhn. Well, Max Kuhn once wrote an article in the New York Times, and he stated, R has really become the second language for people coming out of grad school now. And there's an amazing amount of code being written for it. And this is even more valid, this statement, in 2015 than in 2009. You have already done some R. You have been introduced into R in the previous first course on univariate statistics. Nevertheless, here a really brief overview of what should be familiar with. If you are not familiar with that, take some R basics learning course. There are several courses available for free on the internet, for example, the Data Camp online course or other ones. I leave that to you. You will also have a next slide. I will give you some hints where you can learn more about R. Anyway, you should know that R can be used as a calculator, that you have different objects. The most used ones, most frequently used ones in our context are the vectors, which are assigned with a C, bracket open, bracket close, factor, which you use for categorical variables, a matrix. Matrix is a combination of several variables of the same type, so either all categorical or all numerical. A data frame, where you can combine different variable types, and finally lists, where you can just put in different object types. For example, you can put it in a vector, a matrix, a data frame, and all can be part of a list. You should be able to index objects. For example, you should know that squared brackets are used to index part of an object, so be it a matrix or a data frame or a list. In the case of the list, you need double squared brackets for some objects. You can access a variable with objects $variable or objects at slot, depending on the object type. You should be able to read and write external data. You should also be able to plot basic graphs, and you should be able to write functions, or be familiar with the specific, with the general pattern of functions. That is, function, round brackets, then there's an argument equals something, then you have a comma, another argument, and so on. And finally, you should close with a round bracket. So inside the function, you always use a comma. One of the mistakes people sometimes do is either they forget the comma between arguments, or they use a semicolon or whatever. So these simple spelling mistakes sometimes lead to frustration. So check what you do before you complain that something is not working. Check for spelling errors. And of course, use RStudio, because RStudio will help you if you have forgot a bracket or something. It has syntax highlighting implemented and other features that help you to get along with R at the beginning. Nevertheless, you may have some further questions that you're not able to figure out, and you will need help. You may need help for this. Where can you find help? First of all, there are websites and forums that list a lot of introductory tutorials on stat methods or on Stack Overflow that introduce to the basic concepts. You have teaching videos related to basic steps in R, and you have mailing lists and archives of this mailing list where a lot of questions are asked. So typically, before you ask a question to a mailing list or even to course supervisors or something, check out whether this question has been asked, and you may find it in the mailing list archive. So that teaches you to get familiar with online help and finding help for problems, because this course only runs for a limited amount of time, and when you write your master thesis or later in your working life and still need to struggle with statistics, if you consider this as a struggle, then you're able to search for help yourself. However, of course, when you have some problems with R, you don't find what's going on, and you have to obtain cryptic error messages, which may sometimes be the case in R, then of course you can also ask us course supervisors during the face-to-face lessons. We also have a beginner's mailing list at our university that is exclusively for people from our university. So for first steps, again, before you post something, check whether you can find the solution somewhere else. Otherwise, you may not receive an answer. Feel free to use your own notebook. I mean, if you're from outside of the university, it's obvious that you need to do this. If you are inside the university and follow this course, you can use the infrastructure of the university in terms of the computers provided in the computer room. Everything you need is installed there, should be installed there at least. However, if you need to continue working with R later on during a final thesis, dissertation thesis, or a master thesis, it may be beneficial to have R installed on your computer and be able to run it on your computer. So you can use, if you like, in this course, you can bring to the course a wireless LAN enabled notebook. Should have installed R or RStudio, and I provide you with a package with an R file, R script install packages.r that you find on the course website. It's in the beginning of the website. You find the link, you can download this, and if you run this, it accesses an internet page, reads all the required packages from that page, and installs them. If you need to install further packages, then just run the function install.packages and then type the package to be installed inside the brackets and use hyphens. You can also see two screenshots here of R and RStudio, and if you click on the slides, you will find that I put that there's a hyperlink behind these figures, and you will directly be taken to the website and can download RStudio or R. So this is a lot of topic. These comments so far was just on the organization of the course, on the general course objectives, and now we start with the first block. So we really start with the statistics. However, today you will only revisit statistics that you probably already know. And the reason this is to get you acquainted with learning the course via video online lectures. Also, sometimes some details may be novel to you, and the concept I employ may be a little bit different than in the previous part of the course. What are the learning targets of today? Today's learning targets, first of all, to understand and use basic univariate statistical methods, including exploratory analysis, and to evaluate model assumptions using model diagnostics. We'll have a look into this later on in R, and you can do some exercises in R either at home or in classroom under supervision and with some help. Anyway, you should follow the lecture in detail, and if you have questions, ask next week. So what are the learning targets? What are the study questions related to learning targets? You have them here. I don't go through them in detail. These questions will be asked to you in the next session, and as I mentioned before, students will be randomly selected to answer these questions. So we start with the part on exploratory data analysis. The first step in any data analysis is to look at the data. There's a general principle that says the so-called GIGA principle, garbage in, garbage out. If you put in data that is not suitable for answering your research question, has particular problems, there is no need to fit really fancy statistical models or anything. You can't get something out of messy or non-appropriate data. So what are the different steps in exploratory data analysis? First of all, you should check for outliers. We will discuss outliers a little bit later. That's also the general term here. We will discuss in more detail what different kinds outliers can be. You have checking for homogeneity or variance. That's checked, for example, with a conditional box plot for different categorical variables, as well as for the linear regression model. We will discuss this a little bit more and have a slide overview. Normality, so normal distribution by using a quanti plot. You should be able, you should check for double zeros in the case of ecological data. Ecological data often has double zeros. Why does ecological data have double zeros? Well, when you have species in a site, that's typically what you have. You have columns, species names, and in the rows you have different sites or cases where the species has been, where the different species have been monitored. And you typically have the case that most species are only rarely occurring in your data set. That means you have some species that are very abundant, that will be present in many of the samples, but many species just do not occur. And absence of a species in pairs of sites may be a problem if you, for example, include this in comparison of distance metrics. We will discuss this later. But also, if you have models where you have many zeros in the response variable, for example, you try to predict the abundance of a species, then you need particular method models that are able to deal with such situations. Zero-inflated models as the key word here. You should check for collinearity. That's particularly in the multivariate case, so with multiple explanatory variables, or also in multiple response variables. The relationship between explanatory and response variable, for example, scatter plots, to see whether you really have linearity between them, and to check for spatial or temporal autocorrelation, for example, using variograms. Note that not all of these checks need to be done before you conduct the statistical modeling. They could also be done when you have fitted your model and you're inspecting the residuals, but they are part of any data analysis exercise to some extent, depending on your data and the context. So I won't dwell much more into this because there's a very well written paper that is freely available, and this is a must read. So I'm not dealing more with all these topics here, with this topic here. You may have heard about one or the other of these topics as well before in the course, but you should definitely read this paper, and this paper is actually the knowledge in this paper that is provided is assumed to be known to you, so that could be also a question in the exam. So here just a quick overview. That's really just for showing scatter plots. You have seen a scatter plot before in the course. I guess you have seen a box plot before here, and you have seen a histogram with the density curve and the normal distribution. So the histogram, and we fitted the density curve of the normal distribution in red and the density curve of the data in black. So these kind of plots you should have seen in the course. You should be familiar with them and the interpretation of these plots. If you are not, you would get the related knowledge if you read the paper of Sur that has been linked on the last slide. Also, there are more sophisticated plots than box plots. We will check them out in R directly, and if you read the text to the slides, I always provide, to most of the slides, I provide some additional information below the slides. Some comments. You will find, for example, the link to the bean plot paper, which is also freely available. So the scatter plots we can use to assess linearity or collinearity between variables. Box plots can be used for outlier checking. Some more words on outlier checking later on. And histograms can be used to assess the symmetry of the distribution, whether the distribution is symmetric or whether the data is normal distributed. So we come to the topic of statistical modeling. The aim is in statistical modeling, and this is now perhaps a little bit different to what you considered before. So a lot of people say statistics is, hey, which kind of hypothesis test do we do? But that's not the gist of statistics. The idea is to somehow model data, and either use a model which allows you to use a parametric model, or a model that provides you with parameter estimates, so you can do an inference with other data as well. Or there are also some machine learning procedures, black box models, more or less, that allow you to fit the data and study patterns. So it's not so much about which test should I use for which data, but rather what is the model that can be used for your data that's most appropriate. So our general aim is to fit a model to the data that can be used for some kind of inference. So we want to estimate an interval or a point for a parameter. We want to classify data. We want to do hypothesis testing, compare different estimates or something like that. An example, a very simple example, would be that the arithmetic mean is an estimate of the true population mean. So when we calculate that, we have some kind of model, and we use it for inference of the true population mean, mu, and we have the variance, which is estimated as a proxy of the true variance, sigma square. So the squared standard deviation is an estimate of the true variance, sigma square. Well, if we use a model, of course, every model has assumptions, and we need to check whether these assumptions are fulfilled. So, for example, you have already heard the assumption of normal distribution, the assumption of independence of observations, and we will discuss a little bit more how we can check them. And most models incorporate a deterministic and a random component. In terms of mixed models that you have heard in univariate course, a deterministic part is the fixed effect, a random component is the random effect, and the random part may also be an error part, but is not necessarily an error part. So although we consider this or describe this as error in most parts, at least in the first part of this course, it's not necessarily an error. So an example is the linear regression equation. The response variable is given by b0 plus beta 1 times x plus the error term. You can also describe this as signal and noise. So this is the signal that we model, and this is some random noise in this context. And fourth, so we have selected a model, we have checked the assumptions, we know that we have some fixed effect or random effect in the model, although there are also models that just are deterministic. And in many situations you can fit different models to the data, so it's not directly obvious which model would be the best or would fit best to data. So we need some criterion that tells us how good a model fits to the data, and these goodness or so-called goodness of fit measures are required, and there are different ones of them. So for example, the archaic information criterion, the R-square you certainly have heard about, or the root mean squared error. These are all goodness of fit measures that can be used to compare the goodness of fit from different models. Now we start with the first question or the first objective. Our aim is to compare the central tendencies of two variables in this case, and our question would be, are our sample means drawn from a statistical population with the same mean, true mean, mu? So this is rather abstract, so I show you a short example where such a research question, where we had such a research question and selected a t-test. So the example that I give you here is that we had a study on spiders in the riparian zone. They were in the riparian zone of stream stretches from non-restored and restored stretches. So in each of these stretches we sampled the spiders. And this was done in different streams. And we wondered whether the restoration of these stream stretches may have led to, first of all, of course, a better ecological status of the aquatic community that is directly affected, of course, by restoration measures, and whether, for example, if you have an increased species richness with more larger insects, for example, if this leads to a better body fitness, body condition of spiders. Well, we didn't find a significant difference in the results. Nevertheless, you see here the figure for 9 sites, and this is 10 sites. For 10 sites and 6 sites, we actually had here on the x-axis you have the non-restored section and the restored section. You see that the body condition is in 6 of the sites higher than in the restored section than in the non-restored section, and in 4 streams this is not the case. So actually that should be noted that each of the line is 1 stream. So you have 10 different streams, and in each stream you can compare the non-restored and restored site. What it also shows, the example, just as a minor comment, is of course that statistical significance does not mean ecological significance. In the previous slide, if we just jump back, you would still say, well, there may be an effect, or there is a tendency for better body condition in spiders, even though it's not statistically significant. But you have heard about all the shortcomings of null hypothesis significance testing in the previous course part. So the t-test has certain assumptions. These assumptions are, first of all, that the data is normally distributed. So we can check the normal distribution using graphical inspection. We assume that the data is independent, so all the samples are taken independently from each other, that we have variance homogeneity, so that the distribution around the central tendencies is similar for both types of data, and all these assumptions need to be checked. So we are advocates of graphical inspection. If you want to know more details, I give you a reference on the slide comments in the comment section, I suggest you read Quinn and Keough 2002. However, there are many other books in the main Donald textbook. You also find information why you should not use hypothesis testing, or should rather use graphical diagnostics and prefer them to hypothesis testing of assumptions. So normal distribution is checked with quanti-quanti plots, and note that the t-test is relatively robust against violation of the assumption of normal distribution as long as the variances are equal. If you have homogeneous variances, you should not worry too much about deviations from the normal distribution. However, if you have deviations from variance homogeneity, then departure from the assumption of normal distribution is more severe. There are different alternatives in these cases. First of all, the non-parametric Wilkinson rank sum test or the Welch's t-test, and you will find more about them on the slides comments. Variance homogeneity can be checked with the f-test, although we suggest rather to do a graphical inspection. Nevertheless, this F-test is later also used in the context of ANOVA, so it is to some extent also consistent to use some checking for the variance homogeneity if you do an ANOVA anyway. So ANOVA means that we compare several central tendencies. First of all, again here, the hypotheses that are involved, or the research question, or the statistical question aim would be, are the case sample means drawn from the same statistical populations and have the same mu. So the true mean is similar. We have our observations from which we can calculate the means, and we wonder whether the data suggests that these mean are all the same. That's the null hypothesis, all mu are the same. And the alternative hypothesis that we have is there is at least one mean that is not the same. Again, an example. This example comes from a study which we conducted here in the area in southern Rhineland-Palatinate, which is in the southwest of Germany. Generally, leaf breakdown is an important ecosystem process that provides energy to stream ecosystems, and we assessed this microbial breakdown rate in 29 streams. So we can find more details if you look on the slide and follow the publication or read the publication. And we asked, well, does land use influence the microbial breakdown rate in streams? This was done in 29 stream systems. And what you see is here that you have slightly, or you have compared to agriculture, relatively higher breakdown rates in urban and forested streams or sites and streams compared to vineyards and agriculture. And this was also statistically significant, although just very low, below 0.05. So you see that's very close to 0.05. And you see it's very, very arbitrary. If you had 0.06, some people would say, oh, no statistical significance, no relevance of the results. And that's, of course, not very, that's, of course, not a very appropriate interpretation of the p-value. You should always give the precise p-value so that people can make up his her mind on whether they deem this result statistically significant or not. So let's go a little bit more into the background of this method. You've already had this in the previous course, I guess. When we want to test whether we have the sample means drawn from the populations with the same mu, we calculate the sum of squares. We have on the one hand the total sum of squares, the SSY here, where we just sum up the differences between the individual observations and the total mean. And on the other hand, we have the so-called error sum of squares, where we sum the differences between the group mean, or for the individual group, and the group mean and the observations, and sum these up. So the total variation is given by the treatment sum of squares and this unexplained variation, the sum of the error sum of squares, SSE. So we don't explain the variation around the individual grouping variables, grouping levels. So in our example, that would be, although it's just 3 cases here, imagine we have agriculture, we had urban, and we had forested land use, and each of these land use type would have one of the means. And then we conduct an hypothesis test hypothesis test would here be run with the f-test, the mean sum of squares for the treatment divided by the error sum of squares. In different textbooks, in other textbooks, different abbreviations for sum of squares, for the error and so on are used, different symbols. So you have to check, when you read the textbook, you have to check what is the terminology that is used in the specific textbook. And you will find more information how you can calculate the mean treatment sum of squares and the mean error sum of squares. Although if you use R, I mean, you don't need to do this by hand. What are the assumptions of ANOVA, of analysis of variance? First of all, we assume a normal distribution. Again, we can do this with graphical diagnostics using a quantile plot. We will do this later on in R. The samples should be independent, and that's typically violated for spatial data, where you have a spatial relationship, or for temporal data, if you repeatedly sample from something. In these cases, you cannot assume independence of the samples. And we have the assumption of variance homogeneity, so that can be checked with graphical diagnostics. We deal a little bit more with these diagnostics in the context of linear regression, and they can typically be checked after running an ANOVA. Again, the typical ANOVA with f-test is more robust against violations of the first assumption, so slight deviations from the normal distribution do not influence the outcome as much as violations of the variance homogeneity assumption. And especially the variance homogeneity assumption may lead to an underestimation of the real p-value. That means the real p-value can be several times higher than the computed p-value. So, for example, you conduct a test and you obtain a p-value of 0.02, but under variance heterogeneity, so assumption is violated, your true value for this data may be much, much higher. So you may have a real p-value of p equals 0.3 or something like that. And you conduct an error if you now infer that your results are statistically significant. What should you do in case you have, for example, variance homogeneity or data is not normally distributed? There you have as an alternative the Kruskal-Wallis test or permutational ANOVA, and in addition you have the Welch's ANOVA for data with heterogeneous variances. What you could also do is, if you have a violation of the normal distribution, some authors suggest that you should transform your data. However, I'm not an advocate for this. There are good reasons to not transform data. First of all, you sacrifice some interpretability of the data, but more importantly, there are often statistical models that may be more appropriate. For example, you should not transform data if you can use generalized linear models instead. Finally, you could also incorporate heterogeneity of variances into data due to some spatial or temporal structure. And I give you some more information and literature references on the comments to the slide. And now the final topic for today is the relationship between two continuous variables. We will deal with multiple variables in the next week. That's the classical ordinary linear regression model. You may have heard of this already. I'm sure you had this in a bachelor course and you have seen that. That's the straight line relationship. between two variables. It's a bivariate relationship between an explanatory variable and a response variable. Here we have the response variable y that is given by an alpha plus beta 1 x1 plus an error term, where the error is normally distributed with a mean of 0 and is then in the variance of sigma square. So again, an example, where do you need something like this? Here we have an example from a study where we measured pesticide concentrations in different streams in southern Rhineland-Palatinate. And the issue with pesticides is, especially in smaller stream systems, that their input into stream systems is event-driven. And it's mainly driven by precipitation events. So you should sample the pesticide after or during precipitation events. However, typical monitoring doesn't do that. They just go to the stream once a month, if at all, sometimes more frequently in specific measurement programs. And there are event-driven samplers. However, these event-driven samplers are more tedious and laborious to work with. So the question was, can we use passive samplers? These are some devices that are deployed in the stream and have a receiving phase into which the chemicals of interest adsorb or partition into. And we compare here on the plot the concentration from the EDS, from the event-driven peak concentration against the time-weighted average concentrations from the passive samplers, and we see that there's actually a very, very good relationship between them. Or the data almost follows a one-to-one relationship. And we see here some typical for linear regression model. We see an R squared explained variance that is given for the model. So how do we evaluate the model? How do we calculate the R square? Well, we need to calculate, as for the ANOVA analysis of variance, we already discussed the different sum of squares. We have the same method here. We calculate the error sum of squares. The error sum of squares is given by the deviation, but note that only deviation in the y variable between the fitted regression line and the individual observations. So the error, the measurement error in x is not taken into account. The aim is to minimize the error by the in the regression line. So the smaller the error, obviously, the better this is. And we have in addition the total variation in the data. That's the sum of square of the y. That's depicted in this figure on the right hand side. We see we calculate the difference, again only the difference in y direction between the global mean of the data and the individual observations. Why do we take the global mean? Well, the global mean would be an intercept only model. If you fit a model, a regression model without a variable, that would be a model where you just have the mean. Because if you could say, well, if I don't have any other information on how to predict the response, I just take the mean of the observations. That's my best guess that I have. And there's also an element of manipulation that you sometimes noticed in scientific papers. I mean, it's not necessarily manipulation, but you should be aware how you interpret this. Because if you omit the intercept from the model, so you fit a regression model which goes through 0 and 0, you don't need an intercept term, and then you compare the data, the model without intercept, you compare it to the mean at 0, and the deviation to the mean of 0 is obviously much higher than the global mean of the data. Here, this equation you've already seen in the context of the ANOVA. It's a total variation equals explained variation and unexplained variation, and the explained variation in the case of the linear regression is the explained variance. So you easily obtain this by just dividing the sum of square for the regression by the total sum of square. That's the explained variation that you have in a model. That's something that you probably have heard before, and for the case for the square root, if you use the square root or take the square root of the r square, you have the same absolute value as the Pearson correlation coefficient for the case of correlation. In the case of multiple variables, you should use the adjusted r square. That also takes into account and punishes or gives a penalty for the number of explanatory variables that are included in the model. As you know that otherwise, the more variables you add to a model, the higher your r square becomes. So you have some inflation of the r square if you just increase the number of variables in the model. So of course, the linear regression model also features some assumptions. One of the assumptions, the first one and the second one, the first three assumptions actually are the same as for analysis of variance. You can all check them graphically. So it's normal distribution of the error. It's independence of the error. So we discussed this before. You may have temporal structure or spatial structure in data. And finally, variance homogeneity. You can check this as discussed before for the analysis of variance. You have to check this. And you also have to check the assumption of the linear relationship. So what happens if one or more of these assumptions are not met? Then you have alternatives. For example, you can use a generalized linear model, generalized least squares. You could transform variables, but that's only the case if other models are not more appropriate, for example, a GLM. Or you could use robust regression, and again, you will find more information on these topics in the comments to the slide. You also find information which type of models you can use if you have measurement error in X that should be taken into account. Now let's come to model diagnostics. Here the example of variance homogeneity. We will see again in R how we can fit this. This is just an overview for the time being, where we discuss the different patterns that we may observe. So we have the fitted values of the regression model, but you would also have the fitted values for the ANOVA just as factor levels, not as continuous scale, of course, against residuals. And ideally, you see something like that. This is for a linear regression model, so the data is randomly scattered. So for an ANOVA, you would ideally see a random scatter for each category, for each factor level. So you don't have any scatter along this x-axis. You only look at the scatter of the residuals in the response in the case of t-test or ANOVA. Well, what we see is basically that in the first case we have a strong increase, we have very small variation, and you can see also note the scale of the residuals. We have very strong increase in variation here. We have a slight increase in the bottom left figure, where we have the individuals you see here. Look at the scale again, where you have a slight increase. And we have some pattern that indicates nonlinearity in the bottom right figure. Again, you will find some more information which models to use. We have discussed these on the previous slide, and you will find more information in the comments to the slide. So we come to the next model diagnostics, that's leverage points. So leverage points are a predictor outlier. What does predictor outlier mean? Predictor outlier means it's an outlier along the x-axis. You see here we have several observations between 0 and 10, and they are interspaced by approximately half unit. And the next observation has an x value of 20. So we can see that this influence at this point has a strong influence on the model. It would track the regression line here, so it would be a leverage point and at the same time an influential point. We evaluate the leverage point using so-called head values. We will learn later on in the course, in fact next week, why it is called head value. For the time being, we just should know that head values provide information of the influence of the relevance of the x values on the predictor scale. In the second figure we see here a non-influential leverage point, so this point is very distinct as in the first case. Nevertheless, the data, the model would not be much influenced by this individual point. It follows more or less the same relationship as all other data. So it would be a leverage point, but would not be influential and most likely not be a problem for our model. So what we will look at in R is later on, we will also look at outliers in the response variables, so in the fitted model, and we will consider outliers and leverage points at the same time by using Cook's distance, but more about that when we turn to R. How can we deal with leverage points or outliers? Well, we could either check whether the values are plausible. Sometimes, if you have done field work or laboratory work, you may have simple typos, and that lead to very strange or odd values. And so this is the first step to check whether the data are plausible. Also, you can't have negative concentrations, for example, in the case of chemicals in the environment. You should, if you have the possibility, fit different statistical models to the data or transform the data in case to deal with that, depending on how severe the issue is. And in addition, you could check the robustness of the model results when removing observations from the model. So these are ways to deal with this issue. And before we turn to R, here a flowchart for a simple linear regression model. So again, you start to fit the model, and then you check several assumptions. Note here suggested if you don't have constant variance, to add new terms or transform X or the response variable. Nevertheless, you could also just use a different statistical model, such as a GLM or other ones that may be more appropriate. That depends on the data at hand. Then you check whether outliers or leverage points exist and so on. And you can follow this flow chart this flow chart to conduct a regression analysis. What we will do in R now is we will work with a data set called POSSUM after a short demonstration exercise, which includes biometric measurements of possum in Victoria, Australia. So first we load the data into R and check whether male and female possums have the same total length. So that's clearly an example of a t-test, of a comparison of a central tendency. Then we check whether the head length differ between four age groups of possums, and you are supposed to conduct a linear regression analysis for the relationship of different variables. You will see more details. We will see more details in the scripts.